Okay, I thought first what I want to do is just go through some of the stereochemistry topics and make sure we're on board with that. We talked a lot about stereochemistry that I'm not going to focus on the test. For example, diastereoselective reactions with chiral groups, resolutions of racemase and things like that. I'm not going to worry about. What I want to focus on for stereochemistry is that you have an understanding of the terms we talk about when we're talking about stereochemistry, be able to recognize molecules which are chiral and those stereochemical elements, the relationships between molecules, and be able to determine RNS, okay, the configurations. And that's really what I'm looking for. And so we can talk a little bit about this. So if you recall from chapter 6, there were a number of terms that we introduced to talk about molecules that are chiral. So remember these terms. We've discussed the fact that when you have a carbon with 4 different groups attached to it, that makes the molecule asymmetric, right? And if you take its mirror image, it's not the same molecule. And so molecules which are not the same as their mirror image are what we refer to as enantiomers, okay? So they are exact mirror images of each other, but they're not identical. They can't overlap. And those molecules that can't overlap with their mirror image structures are chiral. Okay, so the term chiral. Molecules which are identical to their mirror image structures are achiral. That's things that don't have stereogenic centers. Okay, or molecules. There are some examples of molecules that contain 2 or more stereogenic centers, an even number typically, because you need symmetry in the molecule. But because the molecule is symmetric, there is a plane of symmetry in the molecule somewhere. Its mirror image has to be identical. We'll see some examples of that. Okay, and then the properties of chiral molecules. What's the one property that we see in chiral molecules that we can detect? It rotates the plane of polarized light, yeah, in one direction or the other, depending on which mirror image it is. Question?
Should we have that formula memorized?
No, you don't need to worry about that formula. No. The specific rotation formula, no. Don't worry about that. But recognize that that's the property of chiral molecules, and that if you have a 50-50 mixture of both enantiomers, a racemic mixture, that property won't be observed because they're canceling each other out. Okay. So no oxidative activity with racemic mixture, but it's a mixture of those 2 enantiomers. Okay, so in terms of the context of all of the isomers, remember there are many ways in which molecules with the same molecular formula can be different. Okay. And so if you look at this tree of isomers, it kind of breaks down the subclasses that we've talked about so far in this class. They're bonded differently, constitutional, but for our purposes here and for this test, we're focused on these stereoisomers. Okay. Molecules which are bonded all to the same atoms, but they're somehow different. Okay. That's because they're different in 3-dimensional space, because they're fixed in a certain configuration, or in some cases, they're fixed in a certain position because of a ring or a double bond. That actually is a type of diastereomer. The cis-trans EZ, whether that's being forced by a ring or by a pi bond that can't rotate. Okay? Notice that those are not chiral molecules necessarily, cis-trans double bonds. There's no asymmetry in terms of its mirror image, but it's a diastereomer because a cis and trans double bond are 2 different stereoisomers that are not mirror images. That's the definition of a diastereomer. Enantiomers are those which are direct mirror images of each other. Everything else, if it's a stereoisomer, is a diastereomer. Okay. Cis-trans we've been saying for quite a while. In chapter 6, we started talking about stereogenic carbons, right? So then we saw that there could be cases with more than one stereogenic carbon in a molecule if you look at a related isomer where one of those might have been inverted but the other not. They can't be mirror images, but they're different. And so that's what we sort of classify under configurational diastereomers. Those that have two or more stereogenic centers in the molecule where they're not all the opposite. One is changed, but not all of them is changed. Okay. Okay, so determining RNS. How many people are still having trouble figuring out RNS? Okay, a few of you. I think the more practice we do, the better it will be. So just to remind you, the definitions that we use to determine whether it's RNS depends on orienting the molecule, looking at it from the right frame, and then looking at the direction that you have to go from the highest priority group towards the lowest priority group. So anybody still have trouble figuring out priorities?
Can we just do one with the double bond?
Yeah, I'll go through an example with a double bond in just a minute. So hopefully you can figure out the priorities, and then you want to orient the lowest group towards the back if you can. So in these examples here, I've shown the hydrogen as the lowest group pointing backwards in those structures. It could be written many ways on the paper. Okay? So this is being able to do this really requires being able to view 3 dimensions well in your head. And sometimes that's difficult. If you can use these other tools like your hands we've talked about, that can help because your hand is a 3-dimension model of that compound that you can look at. So let's take a look at, do I have a blank page here? Okay. So let's take a look at some examples, I think, of determining RNS, and then we'll take a look at some examples of what is the relationship between molecules. So we want an example with a double bond. So let's see. If we, let's say we take, oops, sorry, got to turn my pen on. Let's say we take something like this. I should have made that bigger. Anyway, let's take a look at this molecule. This cyclopentane with an OH group and then a double bond hanging off of it. We can see that this molecule, I've drawn a bold and a dashed line, but is this a chiral molecule?
Yes.
Yes, someone says yes. How many people think this is a chiral molecule? How many people think this is not a chiral molecule? Okay, and a lot of you don't know other way, right? Well, in fact, the example I just drew here is not chiral. Where is there a carbon with 4 different groups attached? Just because I happen to draw it with the bold up and the dash down doesn't necessarily mean that really matters in this case, because look at the ring. In the ring, I have this direction of the ring, around the ring, is the same as that direction around the ring. So if you're looking at this carbon, it actually only has 3 different groups. 2 of those are identical. The rings, the bonds in the ring, those are identical. There's no difference between one side or the other. So would you have been able to recognize that? Okay, so if I want to give an example of a chiral molecule, this one isn't one, but what I could do is say take, let's just put a double bond here. An additional double bond. Now that's a chiral molecule. Because one way around the ring is different than the other way around the ring, and so that carbon has 4 different groups. So its mirror image has to be something different. It's not the same molecule. You can't superimpose it. Question?
So the hydroxide group and that hanging double bond don't have any effect on whether or not you can call it chiral?
There's no asymmetric carbon. So let's take a look at that. That's a good question. Do those not have an effect? Well, they will if there's some way to make it asymmetric. So if we have this, and we have its mirror image, what's the difference? Is there any difference? No. Again, this side and this side is the same, so you could line those up and they would superimpose. Once I make it different, and make this way around the ring different than this way around the ring, now those two groups, this one and this one, are not the same. So then you can't superimpose them. Okay, does that help?
Yeah.
Okay. Well then let's take a look at this molecule, and now I've thrown a molecule that actually has no hydrogen on that stereogenic carbon, right? So it makes it a little bit more difficult to figure out what the lowest priority group is. It's easy if there's a hydrogen, because that's automatically going to be lowest priority. We have 4 different groups. They're not all hydrogens. I'm going to draw this larger in the middle, and maybe it'll be easier. Okay, so hopefully it's easy for you to recognize what is the highest priority group. OH, obviously. So if we're looking at this carbon, the OH has the highest atomic number, so that's priority 1. Now we have our 3 carbons, right? For the other 3 groups. Which of those carbons is the highest priority and which is the lowest priority? It's not so straightforward. Can you recognize which one's the lowest priority? The one on the bottom. It's a carbon attached to 2 hydrogens in the carbon, and the other ones have more than just 1 bond to a carbon. So yeah, the one on the bottom is going to be the 4th priority. Okay? So now how do we think about a carbon double bond or double bonds in terms of priorities? We count them as, if you have 2 bonds between the carbons, then we count that carbon here as having 2 bonds to carbon. And so what you have to kind of imagine is taking that double bond, and here's a CH2 group, right? This is a CH2. So instead of that pi bond, there's a hydrogen here and there's a CH2, okay? And also on the other side, of the bond, you imagine that it's attached to this one, so that's attached to a CHC, if you will. Okay. Sorry, I'm running out of room there to draw. So essentially, this carbon and what's attached to it is also considered on that side imaginary. We often don't have to go out that far, but sometimes we do. Okay. So if this carbon is attached to 1 hydrogen and 2 carbons. Okay? So if we think about that, gosh, I'm running out of room, sorry. Maybe I shouldn't have made that so big. So we have carbon attached to 1 hydrogen and 2 carbons. Okay, that's this one. Okay, how about this carbon? We think about those same way. This one ends up over here, so that's a CHC. Okay. And this one is a, what? CHC also, I think. This is a little bit more tricky. Oh, sorry, that one's bonded to 2 carbons. CHCC. Because it's also bonded here. Okay, so this carbon now is attached to a CHCC. At that point it's the same, but then go out further. This one is more substituted than that one. So actually the double bond in the ring gets a higher priority than the double bond not in the ring. Do you see that? Because eventually you get out to more carbons. Okay. Any question on that? Yes.
And the reason that one ended up high priority was because the carbon on the other end of the double bond was attached to another carbon, right?
Yeah, so this one is attached to 2 hydrogens, and eventually when you work all this out, this one is attached to only 1 hydrogen and another carbon.
Right.
And now that I've drawn all over this, it's 1, 2, 3, 4.
It'd be R, wouldn't it?
So that would be 1, 2, 3, 4. This would be R, and the question is, can you see that? Let me see if I can clean this up a little bit. Make it a little bit more clear. Now the problem is our highest priority group, our lowest priority group is in the plane of the board. That makes it a little difficult because it's not up or down. But what we have is 4th priority here, 2nd priority here, 3rd priority there. The OH is coming towards you. So if you're trying to point the lowest priority group away from you, you've got to look straight down from the top. Then, if you're looking down from the top, the lowest priority group is pointing directly away from you. Okay, that's not always easy to see. Okay, but if you do that, you can imagine OH, then the double bond in the ring, and then the double bond not in the ring, and you're going clockwise. If you're looking straight down. Question in the back?
Yeah, can't you always point your thumb to the first priority group and then do the opposite? Would that always work?
Point your thumb to the first priority group and do the opposite. No, because you never know where the 4th priority group is. You have to point your thumb at the 4th priority group. That way won't always consistently give you the right answer. So if you go point your thumb down, straight down like this, OH is coming out, the double bond on the right is going to the back, and your left hand is curving that way. It's curving from 1 to 3. Okay, that doesn't work, right? You need your right hand to go from OH to number 2, pointing your thumb straight down. Okay, right hand R, left hand S. Okay, that one's a little complicated. Anybody have other examples they want me to do? Yes?
I have a question. So on the test, I know like a lot of the stuff in homework and in the book is like just dealing with looking at the hydrogen, and I feel like that's much simpler than what you just showed.
Yes.
So it is on the test going to be mostly like hydrogen?
Probably.
Okay, solid.
Don't know that any examples will have 4 carbons or 4 different groups. But it shouldn't be harder because all you're looking for is the lowest priority group. That's not always hydrogen. So it shouldn't be hard, but probably not. There will be hydrogens
I think
most
this
likely.
one was just difficult because you don't have a dash or a wedge line or board.
Right.
And you flipped it and made it. So
Yes, and that could be the same thing with hydrogen. A hydrogen could show up without the line or the bold or dash and be in the plane too. So that's why you need to be able to see it, however it's drawn and however it's written. Okay, we'll continue thinking about R and S configuration, but I want to do this when we're trying to compare 2 molecules and get the relationships, because I think we probably should see that as well. So we think about a compound which looks like this. Let's see. Okay, let's take a look at this and compare it to that. Okay, look at these 2 molecules. What is the relationship between the molecules and how do you determine it the most easily? Well, look at what I've done. I've drawn the two molecules, they're isomers of each other, they have all the same numbers of atoms and bonded to the same atoms. I've drawn them differently. It's not apparent whether they're the same or different because I haven't drawn the carbon skeleton the same way. In one case, I put the carbon skeleton all zigzag from left to right. In the second one, I've taken the N carbon and showed it with being back from the board instead of the chlorine being up or down. So how would you easily tell the difference between these two molecules? I would suggest what you should do is figure out the RNS configurations and compare those. If one molecule has all of them opposite, they have to be enantiomers. If one molecule compared to the other are exactly the same, they have to be the same. And if one molecule has only one different and one the same than the other one, it's got to be a diastereomer. So let's take a look at this. So in the first molecule on the left, what's not written there, of course, are the hydrogens. So in that case, both hydrogens are going to the back. Okay, so the hydrogen here going to the back, and the hydrogen here going to the back. I'll put the hydrogens in this one too. Okay, so what's the configuration in the left molecule of the bromine? RS. 1, right? What's second priority? 2, 3. Hydrogen is fourth. It's pointing down, right? Clockwise, or if you use your thumb, you need to point your right hand back. It has to be the R configuration. So that one is R. Okay. The chlorine, 1, 2, 3, that has to be S because it's going counterclockwise. So this has the name, right? The 2-bromo, 2R, and that's where the bromine is, and 4S in the configuration. Okay? It's sometimes useful to look at actually how it would be named. 2-bromo, 4-chloro, so it's 2R, 4S. And then the rest of the name. 2-bromo, 4-chloro pentane. Now, compare that to the one on the right. Well, I hope it's easy to see that this one is identical, right? The bromine looks exactly the same, so that configuration hasn't changed. That's R, so 2R. Okay. How about the other one? So from chlorine 1 to carbon 2 to carbon 3, it's counterclockwise, but the hydrogen is pointing up. I'm sorry, it's clockwise. So the hydrogen is pointing up, not away from you, and you need your left hand to do that. So that's the S configuration. Okay, so it's 2R, 4S. The relationship between them, identical. They're exactly the same. Huh? Yeah, I've just drawn, if they were frozen in those configurations, they would be conformers. I'm not going to ask you about conformers in this test.
They'd just be identical.
So I'd call them identical molecules, yeah.
Can you give an example of ones that wouldn't be identical?
Yeah, I will in just a second. Question in the back?
So would that be a meso compound then?
No, these are not meso compound. This is a chiral molecule. A meso compound has to have symmetry somewhere in the molecule. So I'll show you an example. If, for example, this molecule, instead of chlorine on the right, instead of chlorine here, this is also bromine. That's a meso compound. That dibromo compound is now symmetric from the left side or the right side. And the way to tell that is, you could name the molecule and number it from either direction. You can number it starting from the left, or you can number it starting from the right. And you get exactly the same numbers.
When you're naming this, do Do you put the 2R4S in parentheses and then 2 bromo?
Parentheses, that's a good question. Who knows the details? I don't remember. I would do 2R4S for the chloro one, right? 2 bromo 4 chloro pentane. That's how I would do it, and I think that will be right. I don't know. Parentheses are often used, I think. Is that how your book does it?
I mean, last I checked, R and F are involved in the nomenclature,
Yes. You have to name the molecule with R and S if it's a chiral molecule.
but oh wait.
If there's more than one stereocenter, you have to say which one, which number. You have to indicate the number. If there's only one stereocenter, you don't need the number because it's obvious there's only one stereocarbon. If there's more than one, you have to indicate which one is with which carbon.
Okay, so do put it in parentheses before the name.
Yeah, before the name. And then also number the substituent. Yes. Question?
Okay, so like you said, if they're both the same or identical, if one's different, it's an enantiomer.
No, if they're both opposite, it's an enantiomer. It's a mirror image, then everything has to be opposite. If part of it, I'll show some examples again with this. So let's take a look at this compound, the meso compound that I've drawn on the left here. I'm going to erase this to make it a little more clear. Erase some of this here. I'll just redraw it. Okay, so these are both meso compounds. One is a mirror image of the other, right? Because if you notice this, I number from the left 2R4S dibromo, right? What is the configuration in the molecule on the right? Well, this one is S, and this one is R. How is that the identical molecule? Well, you can number it from this side, 2R, 4S. You can number it from either direction. In the one on the left, I happen to number from the left side, 2R, 4S. Here, I get the exact same molecule because it's symmetric. I can number from the right. 1, 2, 3, 4, 5. It'd be 2R, 4S. Its mirror image is the same molecule. Just take it on the paper and swing it around and line it up. It'd be the same. The way to see that when it's drawn properly, of course, is to see that the way I've drawn this, if you bisect the molecule right here, there's a mirror plane within the molecule. If you bisect the molecule here, this side is reflected over on that side. Okay, everything is reflected exactly in the same position. If you have a plane of symmetry which can bisect a molecule, it can't be chiral. Its mirror image has to be the same.
And those would be enantiomers?
That would be a meso compound. Those are identical. They're the same.
Oh.
Now, of course, sometimes it's tricky. So here, again, you can see this also. There's a mirror plane bisecting the molecule. Mm-hmm.
Why is it meso? Why is it
It's a meso compound because it does contain stereogenic carbons with 4 different groups attached, but its mirror image is the same because of the symmetry of the molecule. And again, another thing that would be a big clue for that is that all of the groups on one side of the molecule is the same as all the groups on the other. So there's CH3 here, CH3 here. If I made it somehow different, if I had an ethyl over here instead of a CH3 on the end, now it would no longer be symmetric. Now you always have to number from the left side because it's the closest substituent. Now its mirror image would be different. Okay, in meso compounds, again, molecules which contain 2 or more stereogenic centers, but they have a plane of symmetry and are achiral because its mirror image is the same. They could be written in many ways. So notice I've drawn these so it's easy to see the mirror plane in the molecule, but I could draw it in a different way, it's not so easy to see that that same molecule would also look like this. That's the same molecule. It's not obvious that there's a mirror plane, again, because I've drawn the carbon skeleton not in a symmetric fashion. I've drawn it differently on the paper, but it's the same molecule. Okay, so that's why I think the foolproof method is to really figure out what the configurations are and compare them, then see if you can name the molecule from either end and come up with the same thing.
So
Yes.
how could you tell that molecule there, the mirror image, is not an enantiomer versus a meso?
Again, if you can come up with the exact same name for the molecule with the configurations, in other words, if you could number it from either end, it's going to be symmetric and have the same molecule.
So
Yeah.
just number it from both sides.
Yep.
And check to make sure. Okay.
Absolutely. That's a good check to see if you have a mesosymmetric compound. Yes?
So, one looking at an enantiomer looks like it, constitutionally and bond-wise identical, except that the R and S is switched around.
That's right.
Enantiomer. Okay.
So an enantiomer would have, well, let me give an example with two stereocenters. Sometimes easy to see them in rings. In an enantiomer, I could just take a look at the mirror image and reflect it this way. Are those the same? Are they different? I could also draw it like this, which is maybe a little bit more apparent that both stereocenters have switched because I've drawn the molecules in the same orientation. The OH, which is up on the left side, is down on the right, and the bromine is up on the left side, it's down on the right. Both of those stereocenters are opposite. The whole molecule has all the stereocenters in one are opposite in the other. It has to be a mirror image. If it's not somehow symmetric with meso, it has to be a mirror image. And again, if you look at the configurations, you can tell. So the configuration at the alcohol stereocenter, here is R, and the bromine is S, and the alcohol here, so R goes to S, and S goes to R. So then you can compare them. It's always good to figure out the configuration and compare them directly and see what's happening. Okay, so that's those are related as enantiomers. They have to be mirror images of each other because all the configurations are opposite. Now if I drew this molecule, that molecule now has R for this stereocenter and R for the bromine. So here we had on the top, for example, this one, we had RS and it converted to RR. One is the same, one is opposite. They can't be mirror images if there's one of them the same. So the relationship, diastereomer, right. The relationship between its enantiomer, the enantiomer of that one, now compare that to that. Here we have SR and RR. It just happens that this one stays the same, that one switches. Okay, so that's also a diastereomer relationship. Okay, does that help get some of these relationships more clear? There's one more stereoisomer for this molecule which I haven't drawn. Which one would that be? We have RS, SR, RR, SS, exactly. That would be the fourth stereoisomer.
That would also be a diol stereo.
So, again, I make this such a mess. So the SS isomer, I'll draw it here, would have OH down, BR up. So the relationship between those two, enantiomers, both are, R becomes S, R becomes S. So those are enantiomers. The relationship between this and this, diastereomer. The relationship between this and this, diastereomer.
With the diastereomer, only one of the configuration switches, only one of the RRS switches.
Only, there has to be, not everything has switched. So I don't want to say only one has switched. If you have 5 stereo centers and 4 have switched but 1 hasn't, then it can't be a mirror image. If 1 is the same, it can't be a mirror image. It's got to be a diastereomer. Okay?
We have to, say you give us a molecule and you'll say how many stereo centers does this have?
That's a good question. Should I ask a question, just can you identify where the stereo centers are? I'm going to ask a question, probably a molecule pointing out where the stereo centers are and ask you to say what the configuration is. I'll probably do something like that. I'll probably have some comparisons, relationship questions.
So will we have to draw that?
You won't have to draw them, no. I won't have you draw them. Okay, any other questions on stereochemistry? Okay, I want to review some of the other material we had. In Chapter 7 and Chapter 8, we're talking about two main functional groups. Those that contain halogens, the organohalides, and those that contain oxygen. That could be alcohols, phenols, ethers. I'm not going to worry about thiols for this test, so I want to focus on the alcohols and ethers. And what we've seen, hopefully you recognize, after we got through Chapter 7, we talked about several reaction types, eliminations and substitutions. And then when we got to Chapter 8, we saw that we also had those same substitutions or eliminations that are happening in the reactions of alcohols. So if you really try to put this all together, it's not that alcohols do this and halides do that. They're all doing similar kinds of reactions under slightly different conditions. And so if you look at that in a little bit broader perspective, I think you can hopefully recognize some of these situations. So first to remind you, to make an alkyl halide, to make a halo compound from an alkane, there are a couple ways we can do that. We can do addition to a double bond. That's not a substitution elimination, but that's an addition reaction. So for example, we can take something like this, and if you add HCl to it, right, you can make a chloroalkane. And you know a lot about this reaction. It's an acid, right? You protonate the double bond. What kind of intermediate do you form? A carbocation. Protonate the double bond, you end up with a carbocation at the more substituted side, right? I'm not drawing the hydrogen I added, but it would end up there. And then the chloride adds to that position. So we can make alkyl chlorides in that way. So the chlorine will end up with that carbocation. Anybody have a problem understanding this reaction? This is best to use where you form a tertiary carbocation. Okay? To make a tertiary halide, this works really well. To make a secondary or primary halide, that's difficult. So instead of trying to start from a double bond molecule, we can substitute an OH for a halogen. Okay? I'm not worried that you know the mechanism of that reaction, but it is an SN2 substitution. To get a chlorine on, you just need to recognize SOCl2 converts an alcohol to a chlorine. And if you want bromine, it's PBr3. Okay, that will work for primary, like I've shown here, and secondary. That's the best method. And so your book introduced that. I will be asking reaction questions, not for you to come up with the structure of the product yourself. I'll probably have a choice of structures for you to choose from for potential products, so hopefully that'll help. Or I might have a list of reagents, and I'll have the starting material and the product, and you choose which reagent best fits. I think you might have had some homework problems similar to that. So if you recognize, what you should think about is recognizing thionyl chloride or PBr3 to get a chlorine from an alcohol or a bromine from an alcohol. You can actually take an alcohol under acidic conditions and add HX, but those are only specific kinds of alcohols. Which ones do you think would work best? Tertiary, right. So if I wanted to make this same chloride here, instead of starting from an alkene, I could start from the alcohol in that position on the tertiary carbon. It'll protonate to OH, you'll form a carbocation. That reaction, alcohol to protonate first, so you get the OH2+, right? When water leaves and forms a carbocation, and then you add chlorine, what kind of reaction is that? Yes, it's an SN1 reaction. This process, SN1. You'll see some more examples. So we can do SN1 reactions not just from halogen compounds. We can do SN1 reactions from alcohols. Okay, so those are ways we can make alkyl halides. We can also make alcohols. Okay? We can make alcohols by hydration or addition to an alkene. So if we take an alkene, again, these work best if we're forming a tertiary carbocation. So I'll use that same example. An alkene, we can add water. So in this case, what do we need to do this? We need an acid. I'll just say generically H+, and we need water. Overall, that's the reaction. So some acid in water. Now, you might recognize that I just added HCl to a double bond to get a chlorine. Whenever we use HCl, HBr, HI, those halogens are pretty good nucleophiles. So if you form a carbocation, they can add pretty well to get the halo compounds. If we want to avoid that, we want counter ions which aren't good nucleophiles for the acid. I've just drawn H+ here, but we want this weak water nucleophile to actually form the bond. So the acid, just for your information, things like sulfuric acid, because the hydrogen sulfate, or phosphoric acid, the hydrogen phosphate, those are not good nucleophiles. So those provide the proton and then end up regenerating the catalyst from the water proton in it. But that is a way, again, to make a carbocation in which then your water is going to add instead of a halogen. And eventually that extra proton comes back off the water. Okay, so water will add, and then that will lose that hydrogen. It'll go back to reform. That minus means it's come off. It'll lose that hydrogen to form the alcohol. Okay? Now recognize that reaction. That reaction is that forms the alcohol could actually be done in reverse. Okay? We can dehydrate. One of the reactions of alcohols is that we can dehydrate and eliminate through an E1 mechanism. The forward reaction is an addition. The back reaction is an elimination. Because we go through a carbocation, it's an E1 reaction. Now, the way to control that, of course, is how much water is present. If you have a lot of water, the reaction will go to the right. If you do this instead with no water and you just add concentrated, let's say concentrated phosphoric acid, okay, the alcohol will be protonated. That protonated alcohol will go break to form the carbocation, and then we can eliminate the hydrogen next to it to form the double bond. So you see the relationship between this forward reaction and the back reaction? They are essentially the same. It's just whether it's in a strong acid only or in lots of water. Okay, so that's one way to make alcohols. The other way we can make alcohols is by starting from a carbonyl compound. Starting from a carbonyl compound, like an aldehyde or a ketone, and adding some nucleophile. We can add a hydrogen nucleophile, an H-, to give that, or, oops, that, okay. So aldehyde gives a primary alcohol, ketone gives a secondary alcohol, because we've added a hydride. And those reagents, remember what they are? Not H- parentheses. Not H2SO4, that's an acid. Yes, sodium borohydride. So again, recognize this reagent is adding this hydride. The stronger one, which will work for this but isn't necessary, is lithium aluminum hydride. So those two, you just think about those metal hydrides as an H- source.
Does that mean a ketone is less stable than a...
Less stable? I don't think it's less stable.
Well, is... Because lithium aluminum is a stronger...
It's a stronger hydride. Since those are reactive carbonyls, either one will react, the weaker one or the stronger one. What lithium aluminum hydride works for that sodium borohydride doesn't is acids or esters. In that case, lithium aluminum hydride can do the reduction, and it goes all the way to the alcohol. Both of these will give the same product, the primary alcohol, so we've added twice, okay? So if you want to make alcohols by adding an H-, those two reagents do that. Sodium borohydride doesn't react with these, acid or ester, but lithium aluminum hydride will. Either will work with aldehyde or ketone. Okay, so again, these are forms of an H-. So if you can get that in your head, that's what's being added. An H- is added once in these cases and twice in the bottom case. Okay. The same thing we can also add, instead of H-, we can add carbon-. Okay? Carbon- in the form of a Grignard reagent. Okay, so any alkyl halide, you can make a magnesium compound from that, and it will add, instead of adding an H, it'll add another carbon. So you can make an alcohol by introducing more carbons. Question?
On the test, you're going to say, like, show us this Grignard instead of, like, guessing.
I would probably say, to make this alcohol, which carbonyl and which Grignard reagent, I'll probably provide the structures. Which set of those will you need to make that alcohol? I think that's how I'll ask the questions.
And then with that, I can't remember, like, what was it, like, the, when you're creating the MGBR is always on the primary or the tertiary, like, which one?
The MGBR could be anything. That's the great thing about a Grignard. You can make a Grignard out of anything. And so the question is, do you need to add one or do you need to add two? If you have two groups of the same in your alcohol, let's say you have CH3 here and CH3 here on my scribbles, you could have made it from this ester by adding two equivalents of CH3 magnesium bromide. Okay? And that works just fine. If you start with an aldehyde and add a Grignard, you still have one hydrogen left, so you have a secondary alcohol. And those are some of the details that you need to think about for Grignards. Where, though, that substitution really matters, let's see, do I have it on the next one? Is when we make ethers. So when we make ethers and when we do reactions of ethers. So remember that alcohols can be deprotonated to make an alkoxide. So I'll just give an example of this one. And if we want to do that, what's the base we use to make the alkoxide? What's the base we use? NaH. That will deprotonate an alcohol like tertiary butanol. Make an alkoxide. I'll put this in for clarity. Now we can do things with this. We can do a substitution, an SN2 substitution of, say, iodoethane. What's the product? An ether. That's because this is a SN2 substitution where the oxygen-carbon bond is forming at the same time the iodine bond is breaking. So the alkoxide is a nucleophile, iodide is leaving group. We formed an oxygen-carbon bond. Okay, question?
Should it just be one carbon?
Should it be one carbon?
Or, no, never mind.
Oh, it's ethyl iodide I added, yes. Not methyl iodide. Now, if I wanted to make this ether from this alcohol, and try to do it this way, it's not going to work, is it? It's not going to work. Why? The iodine is on a tertiary carbon. You can't do, this is tertiary, right there. You can't do this substitution. This is the SN2 substitution reaction. It won't work. Something else will happen. What else will happen?
Like an oxygen be displaced?
Now the oxygen can't attack the carbon that the iodine's on because it's too crowded. That's the feature of an SN2, when both have to happen at once. Instead, what will happen, let me just change the color so you can see it a little bit easier. Instead, what's going to happen, if you think about this carbon here that has 3 hydrogens on it, and all of them do, they're all CH3 groups, so either one, choose one. Okay? Instead of the alkoxide attacking the carbon as a nucleophile, it can take this as a base, take that proton off, and what will actually happen there is an elimination. So what kind of reaction, what kind of elimination is that? E2. The base and the leaving group and the double bonds all forming at once. I'm not going to have you worry about deciding which way a reaction will go. I'll be asking pointed questions like, in this E2 elimination, what's important, or things like that. I'm not going to ask you to have to figure out whether it goes by E2 or E1 or SN1 or SN2. I think there's two gray areas there that are hard to distinguish. So, but this is an example of an E2 elimination where it all happens at one time. And E2 and SN2 competes. It competes when we do Williamson ether synthesis. It competes when we use other nucleophiles. Some nucleophiles are better. Some are more basic. Some are less basic. Alkoxides could be nucleophiles, but they're pretty good bases too. Things like cyanide, Grignard reagents are pretty good nucleophiles. Other things, so if you look at the notes, we had some details about different kinds of nucleophiles and some of their strengths in terms of basicity versus nucleophilicity. So we want to be familiar a little bit with that. But understand SN2 and E2 are similarly related. In other words, the nucleophile in this case, or the base in this case, are reacting at the same time halogen leaves. Okay. Compare that with SN1 and E1. We talked a little bit about E1 just a minute in making an alcohol, or I'm sorry, in dehydrating an alcohol. SN1 and E1 reactions all form a carbocation intermediate. So if you have some leaving group, tertiary substrates, for example this, you could then, right, if this iodide just comes off, first step, nothing else involved, right, you could do two things from there. You could do in SN1, so some nucleophile, water, for example, or alcohol or some other nucleophile can add, just like I showed how to make a tertiary alcohol. So if that's water, SN1. If instead a hydrogen adjacent comes off with some base, could be a weak base like water, that's E1. Forms the carbocation. We can form the same carbocation from a double bond by adding acid, right? The feature of this is that you have to form a carbocation. So this only works with tertiary substrates. But the competition between adding something, a substitution, or eliminating that proton to do with the double bond formation, that's the gray area. Again, I'll ask very specific questions so you know which process it is, but be familiar with the details of how an E1 works and how an SN1 works. Okay. Alcohols, if you protonate an alcohol, you form an OH, H2O plus on there. As I said, the reverse of this with an H plus. You form a OH2 plus and it comes off, and then you can form the carbocation. So you can do substitutions elimination starting from alcohol, starting from iodide, starting from ethers. So if we do this, you can protonate that OCH3, methanol can come off, and then you could either add chloride to make the chloroalkane, or you could eliminate the hydrogen to form the double bond. E1 or SN1. Okay. So E1, SN1, whenever you form a carbocation, it's planar with an empty p orbital. And so if there were any stereochemistry there, it's lost. The information is lost. If you do a direct SN2 substitution, if you have stereochemistry at the carbon your leaving group is on, it inverts. Okay, that's the other detail to remember about substitution. So if you compare the details of these, I put this in that summary that I handed out. The table is a little different in the notes from class. Gives you some idea about the substrate substitution, a little bit about which things are favored, and I would just say E2, whenever you have alkoxides or hydroxides, that's a good bet that elimination occurs. So think about double bond formation. Inversion for SN2, racemic products if there's stereochemistry involved in SN1. Okay? Any questions about that? So I want you to keep in mind the features of alcohols and halides. Even though they're in separate chapters, a lot of the reaction details that they do are similar.